Welcome everyone to this lecture. So in this lecture, we'll just be looking at something that is called rotation. Rotation. Okay. So this is different from circular motion, which is the previous chapter that we just did. So in the circular motion, you generally have an object. Then this object is just moving in a circular path. Basically, that's what is happening. All right, so you just have an object moving in a circular path. They could be moving with that tangential speed, so they will be moving in that direction, right? So they'll be moving is it anti-clockwise? Yeah, this is anti-clockwise. All right, so this is a circular path. So when this person is actually moving, or this object is actually moving, they are not spinning or anything. Okay, so that's basically how they are moving. So they are moving around in that circular path. However, when it comes to rotation, you're actually looking at the whole body. Okay, so you're looking at the whole body, then the whole body is actually rotating, meaning that it's moving in this circular manner, but the whole body, meaning that each and every mass in this body is actually moving. Of course, when you break it down, and then it's just rotating about this point. Now, this point generally is known as the point of rotation or the axis of rotation, or is sometimes known as the pivot as well. It just depends on how people look at it. All right. So you're looking at the whole body here, that is actually rotating. So every part of this object is moving. All right, and it's moving in a way that is actually circulating about this point. So it's rotating at about this point. That's basically it. Of course, if you break it down, I mean, if you just track this mass, because remember, every rigid body, for instance, is made up of mass, so it's just a sum total of mass. Of course, if I track this mass as it's rotating, it is actually moving in a circular path. Another mass here is moving in a circular path. Another mass here is actually moving in a circular path. All right, as that's basically all of these masses are moving in a circular path, in circular paths. So that one is something that you can actually note. But when you sum all of the masses that are actually moving in these small circular parts, basically you end up with the whole body rotating about an axis. So that is just the difference between rotation and circular motion. Now another thing, of course, they are related somehow, because it has to do with circular. It's circular in a way, all right. And then another thing that we have to differentiate is the point of rotation or the axis of rotation may be moving. So you could have it as fixed. So when it's fixed, you just have this as rotating in that direction. But you could also have it moving. For instance, think of a wheel. So when you have a wheel and it's moving in that direction, after some time it ends up here. So there's two types of motion here. There's the motion that is actually moving with speed v1, v0. v1 is fine, then we say v2. It covers the distance x. This is translational. So it's moving from one point to another. This is a translational. Then there is how it's moving. How it's moving is basically rotating. All right, so it is basically rotating maybe about a certain point. It just depends, so it could be rotating, but this point of x is actually moving. It ends up somewhere here after some time. All right, so it is rotating and it is moving. All right, okay, so you can actually have that you can have it fixed. So this one is fixed, and then here, and then this one, the point of rotation is basically moving, or the axis is actually moving. All right, so this one is a combination. It's normally used as well when we talk about rolling objects that are rolling. That's how basically objects will be rolling as well. All right, so let's just revisit the cycle. So we won't discuss too many things now. We're just going to actually just convert things into another measure here. All right, remember we defined the circle in our previous chapter. We said that if I have a circle, all right, if I actually, so this is the radius, there's my radius. And then we said that if I move from here, to here, and then basically this is my arc length. All right, this is r, this is r, and then we said that this is going to be theta. Now what we said was that theta is going to be s over l. Now what I didn't tell you is that this ratio here is actually measured in radians. I didn't tell you that. All right, such that if s is equals to r, then theta is actually equals to 1, and this is basically the definition of 1 radian. All right, now for 1 revolution, we already know what is a revolution. For 1 revolution, we know that the distance that we actually going to cover, right? For 1 revolution, it means that s is going to be equals to 2 pi r. We know that. So what is theta for 1 revolution? Theta is going to be s over r. This is going to be 2 pi r over r. So you can say that for 1 revolution, theta is going to be 2 pi, and this is already in radians. So what are these radians? So most of you are used to using your calculators in degrees. So in school, you were taught to actually get angles in degrees. Even the protractor has degrees, and basically we've been dealing with degrees all along. So now in these sections, you would have to convert your degrees into radians. So how you do that, if you have a pencil calculator, you just basically do the shift, and then you go to mode. Then you'll see, for instance, it says 1, it's math, it's mth. I think this is 10 or IO, I'm not sure. And then there's 3 dark, and then there's 4 where it says red. So you should choose 4. Once you choose 4, for instance, it means that the angle that you include whenever you're using cos or sine is going to be in radians. For instance, to test this, we know that in degrees, sine of 30 is going to be equals to half. We know that, like sine of 30 degrees is going to be equals to half. So what you do in your calculator, if you have a calculator, just press shift, and then afterwards go and press mode. All right, and then afterwards just press 4. Once you do that, you'll notice that on top there is going to be r. It's no longer going to be d. You'll see a letter r. Now go there and just input sine of 30, right? Then you'll see that you will not get half. You will get another number. You will get another number, which is sine of 30. For instance, you will get that this is going to be minus 0.988, blah blah blah. So I'm going to stop at 988. But then if you want to actually, so it means that the angle 30 here is no longer degrees. This is radians. So you're saying sine of 30 radians. But here you were saying sine of 30 degrees. That's why you could get half. All right. So there must be a number that actually corresponds to this 30 degrees, and then such that if we include that, if we put that angle, it is an equivalent in radians of 30 degrees. Okay, so we have to find ways and how can we actually convert everything like that. So we know that for 1 revolution, we know that theta is equals to 2 pi. We also know that for 1 revolution, theta is equals to 360 degrees. So this is radians and this is degrees. So which means that 360 degrees is the same as 2 pi radians. Okay, so if I say that, and then basically I divide by 2 both sides, and then 180 degrees is the same as pi radians. So this is what I'm going to actually use to convert everything. Okay, so now let me revisit the example that I had of sine 30, and then what I'm going to do now is, okay, so I know that sine of 30, if my calculator is in degrees, I'm going to get half. So how do I get my calculator in degrees? If you want to get it back in degrees, your Queso calculator, just say shift and then say mode, and then just press 3, and then you'll see there on top is going to have a D letter. So you know that now it's in degrees. Whatever angle that you put, whether you're using sine, cos, or tan, right? So this is only working, it only gets recognized when you're using anything like cos of whatever angle, sine of whatever angle, and 10 of whatever angle. When you say 1 plus 1, it doesn't matter whether your calculator is in degrees or radians, it's still going to give you 2. But once you start using sine, cos, and tan, and then it's going to start actually looking at it whether your angle is in degrees or is in radians. So if you have it in degrees and you say sine of 30, it's going to say half. So let us find out what is 30 degrees in radians. Well, we can use this factor to this fact, so we know that pi radians is going to be equals to 180. So basically this is 1 over 6, which means that 30 degrees is going to be the same as pi by 6 radians. So change your calculator into radians now. You say shift, you say mode, and then you say 4. It is now in radians. Then what you do now, just say sine, and then just say of pi divided by 6, and then you get half. So meaning that now when you say sine, instead of 30, you use pi by 6 because now you want radians and the equivalent of 30 degrees in radians. Then you'll get half. So which means that pi by 6 radians is the same as 30 degrees. Okay? So if you're using degrees, you're going to put 30. If you're using radians, you're going to put pi by 6. That's basically what it means. Okay? So you're basically converting the two. All right, so that's how you can convert from degrees to radians. It's probably going to be easy for you guys to go backwards. I mean, for instance, if I was to ask you to convert, maybe if I say to you convert 5 pi over 4 into degrees, all right, so it's very easy. You're just going to say 5 over 4 and then you say pi. Then because you want to get rid of pi, you're going to say radians. This is in radians, so this is in radians. You want to get rid of red, so you're going to say pi rad is 180 degrees because you want degrees. So you can see that this is going to cancel this, so you have 5 over 4 multiplied by 180. Whatever answer I get is in degrees, and I get that my angle is going to be 225 degrees. Okay, so hopefully you guys can actually understand this. So just the special cases, for instance, so 360 is going to be equals to 2 pi, and then 180 degrees is going to be equals to pi, and then 90 degrees is going to be equals to pi by 2. These are just the special or some of the common angles that you're going to actually have. So this is degrees and then this is radians. All right. So this is important because from now on we are going you have to change your calculator to radians. So what I would advise you now to do is if you're doing this section, make sure that your calculator is in radians. So make sure you do shift, you do mode, and then you actually do 4, which is radians. So if you're using a different calculator, I don't know how to do it. Here in South Africa, we generally use the Casio calculator, so the scientific calculator. So we generally, that's why I'm just using that one to just instruct. I honestly don't know how to do it with other calculators. All right, so if I have an object, there's my object, right, and my object is moving in this anti-clockwise direction, so at some time it's going to be somewhere here, so it's covering this circular path. Okay, so it's rotating in this case, right? So we can actually find the angular displacement. All right, so this position, if I call it theta 0, because this is theta, if I call it theta 0, it could be 0, it could be anything. This one, the way I drew it is not actually 0, and then this is theta 1. So after some time it's going to cover some, this is the arc length that is going to cover here. But then if you want to know what is going to be a change in theta, is going to be that distance, and that change in theta is actually known as the angular displacement. Okay, so basically that's the one, and it is measured in radians. All right, so it's always measured in radians. So it basically gives you the position in secular or in secular quantities, basically, or angular quantities. That's the right word that we normally use. All right. So that is the angular displacement. If I know how long it takes to move from this point A to point B, let me just call this point B, to move from this point A to point B, I can actually find the average angular velocity. So this one now is angular velocity, and this is basically going to be given by delta theta over delta time. So I mean, this is simply like v is equals to change in x over change in time. So when you are having it moving in a straight line, but now because you have it moving in angular or in secular path or direction, in a way, you then don't have it as v, you actually have it as omega. This w is called omega, and then this is basically the angular velocity, and it's measured in radians per second. Those are the units for this one. We can, in actual fact, if you just take the magnitude of that, it's just going to be that, and then you actually just find the angular speed. This one is the angular speed, just the magnitude without any direction. It's just the angular speed. Now, in terms of the direction, you just take whether it's rotating clockwise or anti-clockwise. I normally choose anti-clockwise as positive, which means that if I get a negative, it means that it's moving in the clockwise direction. That's what I normally choose. I mean, it's up to you. Generally, different textbooks also use different conversions as well. So I generally use the anti-clockwise as positive unless I state otherwise. Okay, I can find the instantaneous speed. So the instantaneous speed, which is the speed at that instant, is given by the limit as delta t tends to 0, and this is basically that limit of delta theta over delta t. So if I find the limit is very close to that instant, I'm basically going to get what delta t is. All right. Okay, so let's just do an example. There's an EG, there's an example. So basically I have a body that is rotating. So if I was to place an object here, this object would just move. After some time, it will find itself somewhere here, and then this is basically going to be delta theta, and then this is theta 0, this is theta 1, and then I'm telling you that just to move there it took about 2 seconds, right? And it's moving at a constant angular speed. So the angular speed, assume that is constant, so we can use the average angular speed. All right, so we can just find out what is delta theta from this one. All right, so let me just give you the angular, and then maybe this one is 3.5. Now I'm going to give you as revolutions per minute. All right, and I'm telling you that it's constant. All right, we can find this because this over delta time is going to be omega. All right, so which means that delta theta is going to be omega multiplied by time. Okay, so how will I be able to actually change that? So how you do this is you just say omega is 3.5, and then you say rev per minute, and then you just open that, and then you say 1 rev below. It's going to be 2 pi radians. Okay, and then you're going to change the minutes into seconds, and then this is basically going to be 1 minute is going to be 60 seconds, and then you basically change that, and then it's going to be in rest per second. Okay, so it's going to be 3.5 multiplied by 2 multiplied by pi multiplied by 1 over 60, and then that basically becomes 0.37 radians per second. All right, okay, so this is going to be 0.37, and then the time is said is going to be 2 seconds, and then we can just find out how many radians that's going to be. 0.37 multiplied by 2, that's 0.74. Okay, this is radians per, oh sorry, it's just radians. All right, so that's that. And then if you want to know how many revolutions are going to be covered in this time, it's a bit easier. So you could just say, let me just make a line. So you could say theta is just going to be equals to 0.74 radians, and then you just do the opposite of that. So you know that 2 pi rad is 1 rev, and then you're basically going to get theta, how many revolutions is actually going to correspond to that. So 0.74 divided by 2 pi, 0.1 0.12 revolutions. Okay, so you could find a number of things, but then I think this is just enough. We don't want to do a lot of things. All right, so what about the angular acceleration? Can we find the angular acceleration? So this is a situation whereby something is rotating. Let's just say it's rotating anti-clockwise, such that if I put an object, now generally what you do is you just put a small object just to track motion. That's all I'm doing. That's why I'm putting some objects here. So basically it's going to have omega 1 here, omega 2, whereby they're not the same, and then over time. So you find something called angular acceleration, and then this is actually going to be equals to the final angular velocity minus the initial angular velocity over change in time. And this is just, in this example, is just going to be that over change in time for that example. Now the units for this is radians per second squared. Okay, those are the units. Now if this angular acceleration, right, because this is the angular acceleration, if this angular acceleration is constant, right, we can do a couple of things. If this is constant, we can actually find, similar to how we found equations of motions, we can say the final speed or velocity in this case, because if it's negative you have to substitute the negative, the initial velocity plus this delta t. Now if you check it, this is similar to this one, final speed initial speed plus at. So this is when you are actually moving in a straight line, and then this is when you are actually rotating. Okay, so you can see that they look alike or similar, not right? So you can guess by now that I can then do this initial squared to alpha delta theta. This is the same as vf squared vi squared plus 2a delta s. Right? If it's in the x, it's going to be delta x. If it's in the y, it's going to be delta y. So delta theta substitutes that displacement vector. So you could also use delta theta is going to be equals to initial velocity multiplied by time plus half that time squared. I mean, this is the same as delta s is going to be the initial velocity time half a delta t. So you can see a and alpha, somehow they seem to be substituting one another in this case. We could also find delta theta by saying it's half the final plus the initial multiplied by t. So even this one you could find it and say this is half, sorry, not omega, this is delta s is the same as half the final speed initial speed delta t. Okay, so you can actually see that these things are actually very similar. The other one is just in the rotation, it's rotational. The other one is basically translational or linear. That's how you may think about it. So we can do an example on this. For instance, with EG, we can do an example on this. So for instance, if I have an object that is rotating, it's a rigid body, and then it takes some time, delta t, to cover something. So it covers, it moves from rest, radians per second, and then after some time it will be somewhere, it will reach a speed of 9.5 radians per second, and then it will take about 5 seconds to reach that, to take about 5 seconds to reach this speed. And so I could find a couple of things. I mean, I could find how the angular displacement, it could be covered, it could have covered there. All right, so we could find that. Let's just maybe find first the alpha. Let's just find alpha. So alpha is very simple. It's just going to be omega 1 omega 0 over the delta time, which is 5, and this is basically going to be 9.5 minus 0 over 5. So omega is just basically 9.5 over 5, which is going to be equals to, this is going to be 1.9 rads second squared per second squared. Now that I have that, I can actually find this if I want to. I could use different equations in this case because I know it. So I could just say 0 delta t plus half, since I know this now, and then I just say delta t squared. Did I put the delta t squared here? I had a feeling that I forgot something. So there should be squared there. I sometimes do forget it. All right, and then this is just going to be 0, and then this is 5 plus half, and then 1.9, and then is it 1.9? Huh. Oh yeah, it's going to 1.9. Okay, and then this is going to be 5 squared, and then that basically becomes 23.8. This is 23.8 radians. Okay, we could also find it, you could find how many revolutions are covered per unit time. I mean, you could do that. So it's not going to be very difficult for you guys to do that. But the most important thing is just to show you how you can actually use this. So it's used very similar to how you would actually do kinematics, equations of motion in a straight line fields. Basically, it's more or less similar to how you would approach it. All right. So let's take another concept. Let's look at other concepts. All right. So we can actually relate these angular concepts to linear concepts. For instance, if you think about it, right? If you're in a bicycle or a car, if you're in a car, there's your car. Right, I know it's an ugly car. So as your wheels are rotating about this, they are actually moving. So your car somehow finds itself somewhere, right? And then the wheels are somewhere there, but so they were rolling. So you can see that as you are rotating, there's a road here. So as you are rotating, you are actually covering the speed v. So there must be some relationship between you rotating, because your wheels are rotating that way. I mean, right? So they are rotating about this axis here. They are rotating that way. So since they are rotating that way, they are actually heading in this direction. Okay, so you can actually say this, that somehow I should be able to actually relate these things. And even the very fact that they look so similar to the equations of motion tells you that somehow I should be able to actually relate this. All right, so let's just look at what I have. So for instance, if I have this, right, so maybe I'm here, starting here with v0, I'm somewhere there sometime with v1. Of course, I would have covered delta theta. That's the distance that I would have covered. All right, so I mean, we said that this is an arc, so it would take me some delta time t to cover that arc s. So let's look at this now. So we know that delta theta is going to be S over R. I mean, this is something that we know. So which means that S is actually going to be delta theta multiplied by R. Okay. But we know that the speed V, I mean, if we wanted to know what would be the speed of any object moving from point A to point B in a linear fashion, it's just going to be equals to whatever, even not linear, even here, if I just wanted to find out what's going to be the speed as it's actually moving, that the speed is just going to be given by whatever the arc, which is the distance, whatever distance that they were going to cover, divided by time. All right. But then if I do that, for instance, and I substitute, this is delta theta divided by delta t multiplied by r, but this is omega multiplied by r. Remember, this is the same as omega. So first equation, there it is. This is the only one I'm going to derive. The other ones I'm not going to derive. I'm just going to give it effects. All right. So what else do we know? We also know that for one revolution, 2 pi r over t is equals to this. So I could equate it and say V is WR. This is going to be 2 pi r over t. So you can see from here, I can find that t is going to be this. This is going to be very important. Also, when you are doing oscillations, you are going to use this equation. If you substitute t is 1 over f, which is 2 pi over omega, you'll find that omega is going to be 2 pi f. These equations are very important. I mean, we are going to see them again when we are doing oscillations. All right, so please note these equations and refer back to these notes as well to understand where they will be coming from when we actually use them. All right, another one is AR. AR is V squared over R. So V squared is WR over R, but this is squared. And then basically I end up with omega R. So I can even relate the centripetal acceleration. The centripetal acceleration is related as long as I know omega. I can actually even find the centripetal acceleration. Right? Remember, rotation in a way you could think of it like it's circular motion. It's just that it's every particle of that body is moving in a circular motion. You're just adding up that circular motion. That is why you could actually even relate the centripetal acceleration with that. All right? Because remember, if a body is actually rotating, I could put a very small object here like a fly, and then the fly, as the body rotates, the fly is going to actually move around as well like that. Okay, so you'll see, I'll do one example. So the tangential acceleration is going to be given by this, right? So I'm just going to bring all of them. So these are the important equations, which is that, and also this one. AR is going to be, let me use capital letter R because I've been using capital letter R. This is omega squared R, very important. This one V is going to be equals to that, very important. This one omega is 2 pi f, very important. And from this you can get the period one, which is period is 2 pi over omega, very important. Okay, so these are the equations that you're relating linear quantities with angular quantities. All right, so we can just look at different examples again. For examples here, I don't expect you guys to get very difficult examples. Of course, everything in physics can be complex, to be honest with you, but then generally it just depends on how the lecturer actually does it. All right, let me say, for instance, you have something that is circulating in a clockwise direction. So in this case, I'm just going to choose clockwise as positive just to avoid all of that. So it's going to start maybe somewhere here with V0 of 15 meters per second. Maybe at some point, let's just say here, I'm not sure if it's going to be there. It's going to be 25 meters per second. And then, of course, I mean, if you write the center here, this is that. This is that. You can see that my delta theta is going to be this one. It's not going to 180. So maybe let me just say it took the time that it took to move there from point A to point B is 0.78 maybe seconds. Yeah, maybe let's do that. All right, so I could find the different quantities. For instance, I could find the omega, which is going to be equals to omega. All right, so I don't know what's going to be omega 1, so I could find omega 0. Omega 0, I could find that using the fact that V0 is omega 0r. So omega 0 is going to be V0 divided by r, which is 15. Now let's just give you the radius. So let's just say r is going to be, let's just say 55 centimeters, which is 0.55 meters. So if we do that, this is going to be 0.55. Okay, so this is just going to be 27.3 radians per second. I could also find omega 1. This is basically going to be V1 over R, which is 25 over 0.55, and this is going to be equals to 45.5 radians per second. So that's the one. And then what else? So now I can find omega because I have that. So I could say omega 1 minus omega 0 over delta t. So over that time, that's going to be 45.5 minus 27.3, and then this is divided by 7.8. So my alpha in this case is given by 2.3. Okay, so you could find that. Let me just verify this one if I'm correct. Okay, it's correct. Okay, so I mean, you could find a host of things. For instance, if I say what is AR, maybe at point B, so you could find AR at point 1. That is just going to be equals to V1 squared over R. If you didn't have V, you could say omega 1 squared multiplied by R. You could also use this one. You're gonna get the same answer. It doesn't matter. So let me just say, let me just use the omega 1 because I just want to use the angular quantities. So this is just going to be 45.5 squared is 0.55, and that is going to be equals to, so it's a very big number, 0.7, that's meters per second squared. That's a very big number. You could also find the tangential acceleration, which is basically that, and this is 2.3 multiplied by r 0.55, 2.3 multiplied by 0.55, and that's basically 1.3 meters per second squared. I mean, this one you could verify. I mean, you could say 25 squared, and then you just divide it by 0.55. Should get the same answer, 113. So yeah, it's just 113.6. So it's just a rounding of errors. It's fine. It shouldn't affect that much. Generally, you would expect, because I cut it, I said 0.5, and then that's why I'm getting 3.8 instead of 3.6. All right, so don't worry too much if they are not exactly the same. It's just because I rounded off, that's why. Okay, another nice example to just consider so that you understand the tangential velocity. Let me say I have a disk. There's my disk. Okay, there's my disk. There it is. I'm rotating this disk in this direction. If I put a fly here and I put another fly here, so this is R1. Maybe let me just say R1 is going to be 4 centimeters. And then R2, which is going to be this one. Let's say R2 is going to be equals to 10 centimeters. All right. So basically, I want to find out which one has to move faster? Maybe if they have to get to this point here, if this is point number 1 and this is point number 2, which one will have to move faster? So of course this one is going to move that way. So there's the tangential velocity v1. Even this one is going to move on this path. There's this path that will be taken by this one. Okay, so what is going to be that path? So we want to know which one is going to move faster. So we need to find out what will be v1 and v2. So v1 is just going to be equals to, if this disk is rotating with omega of 18 radians per second, so this is, so the disk is just having the same angular velocity because rotating with the same angular velocity. This is just going to be that, and then you're going to use r1. You can see that this is going to be 18 multiplied by r1, 0.04, and then this is going to be equals to, this is going to be 0, that meters per second. Now what about v2? V2 is just going to be omega r2. This is going to be 18 and then 0.1. Okay, so it should be like 1.8. This should be 1.8, I think. All right, so this is meters per second. So you can see that this one has to travel very fast in order for it to make up for the large arc that is going to travel. Whereas this one, I mean, if you check the arc that this one is going to travel, the arc is shorter. So it doesn't have to be fast because they are both they are both starting here and reaching here at the same time. So if it took 5 seconds to get there, it would take 5 seconds for this one to move there to here. It take 5 seconds for this one to move from here to here. I'm not sure if it's taking 5 seconds, just making an example. All right, okay, all right, so far I think so good. All right, so there is another concept when it comes to rotation. Let me just say I have a board, an irregular board is fine. All right, and then there's a center where it's rotating about this point. If you look at this, for instance, I've touched it on this, there are masses. I mean, this material is made out of small masses. These are atoms, of course, so it's made out of small masses, such that if I draw this one, this is r1, this is mass 1, this is r2, this is mass 2, this is r3, this is mass 3, this is r4, this is mass 4. I mean, I think you get the gist, right? R5, and then this is mass 5, and then R6, and then this is mass 6. So you find something that we call a moment of inertia for each and every particle is going to be given by the mass of whichever mass I multiplied by Ri squared. So an example would be, for instance, for 1 it would be m1 r1 squared. For 2 is going to be m2 r2 squared, blah 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 blah. So I could actually find the total moment of inertia. So this I is called moment of inertia. Now you'll see in the next chapter, this tells us whether something is going to be very hard to rotate or not. And it sort of gives us a measure whether something will be very hard to rotate or not. So this is just measured in kilogram meter squared. That's basically, those are the units. So the total inertia would be the sum of all the mi's and the ri's squared. All right, so I mean, this is just like m1 r1 squared plus m2 r2 squared plus blah 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 blah. All right, so now you can do some calculus whereby you do some integration and all of that. I'm not going to show you here. I'm just going to give you the results. For instance, if you have a sphere, there's a sphere, so I'm not going to draw it properly, right? There's a sphere. If I'm rotating this sphere about this point, I want it to be the center at least, and it's a sphere. There's a sphere, I'm rotating it about that point. Of course, the radius of the sphere is r. It has a radius r. Okay, the moment of inertia for this one using calculus can be found. This is mr squared. All right. If, for instance, I have a very thin rod, it's a long, thin rod, and it's rotating about this axis, the moment of inertia for this one is 1 over 12 mr squared. So m being the mass, right? Whatever the mass is. So it matters how you rotate it. For instance, if I take the thin rod again, and then I just do that, this is the inertia is just going to be 1 over 3 mr squared. So you could see that it depends on the geometry, and then based on the geometry, it also depends on where you are actually rotating, and then basically you do get different moment of inertias. So where were you going to get this? I mean, different textbooks. If you get a university textbook, any university textbook, it will have these values, right? And then we had to derive them. If you're doing physics major, chances are you would have to derive them yourself. You may have to learn how to derive them. So it just depends. But generally, for this course that I'm teaching now, in this channel, because I'm not doing calculus-based physics yet, so I'm not doing the physics for physics majors. I'm just doing physics for applied sciences, like your chemistry students, like your biology students, and so forth. Especially here in South Africa, and then that's basically the type of physics that you would expect to do. So since we have the moment of inertia, you'll notice that when you are actually rotating, you actually have some energy. If you're rotating with speed w, so you are actually having some energy. So we can define the rotational kinetic energy, and this is just basically given by that, the moment of inertia multiplied by the angular velocity squared. Okay, so let's just say I have sort of a cylinder. Okay, so let's just say r is going to be 0.15 meters. Okay, so that's my r. Then it's going to rotate that way. So v0 is 5 meters per second. After some time, the cylinder will be here. And I want you to find v1. Okay, then I'm telling you that the mass is going to be equals to 5 kg. Okay, so what you'll notice here is that there is going to be rotational kinetic energy. There's also going to be translational kinetic energy. And this is going to, if I ignore friction, this is going to be, this is before, and then afterwards, there's rotation afterwards, there's kinetic afterwards. All right, this is half moment of inertia, omega 0 squared, whatever omega 0 is, and then here, whatever omega 1 is. Okay, plus half mv1 squared, this is half I omega 1 squared plus half mv1 squared, this is 0 squared. The halves are going to cancel. Now, since this is a cylinder, basically since it's a cylinder of radius r, there it is, it's a cylinder of radius r, the moment of inertia is given by half mr squared. So just assume that this is a cylinder. All right, I'm just making it a cylinder rotating about the center. All right, and then that's what is going to happen. So I could actually substitute this goes away, and then if I substitute it here, it becomes half mr squared. Now where I see omega, I put v0 squared over r, not capital letter, over r squared. I'm getting this from the fact that omega is going to be v over r, because v is omega r. Okay, and then plus not half because it's gone, v0 squared. This is going to be equals to the same half r squared v1 squared over r squared plus mv1 squared. Okay, so the r squares are going to cancel, the r squares are going to cancel. What about the masses? The masses are going to cancel as well, the masses are going to cancel as well. So I'm basically left with half v squared. So basically it's half v0 squared plus v0 squared is going to be equals to half v1 squared plus v1 squared. So many ways to do that. I mean, it's just like 3 over 2 v0 squared, and then this is basically still 3 over 2 v1 squared. So you could say that v0 is going to be the same as v1, and this is because, I mean, there's no friction here. You just have whatever your initial speed was, and so basically if you're not applying any force, you're expecting that there's nothing that is going to change. All right, but the important thing here is just the approach. Maybe the nice problem that you could explore would be a problem like this one, whereby I have an inclined plane. Let me draw it like this. And then in this inclined plane, I have sort of like a rod. So it's rotating about this axis. It has radius r, so it's going to go down until it reaches this point. And then basically it's rotating about that, so it's going to go down. So if I tell you that it started at rest, for instance, so if I was to tell you that this is actually starting at rest meters per second, and I want you to find the final speed v1 here. Okay, and then this is the height h. I don't know, maybe let's just say the height is 2 meters. All right, and then I might or might not need the mass. We'll just see the calculations. If I need the mass, I doubt we're gonna need the mass. If we need the mass, I'm just going to give you the mass. All right, and then let's just find what's going to be the speed. Now we have to find the total energy before and the total energy after. Is going to be the same if we ignore friction. Okay, so if we ignore friction, it's going to be the same. If there are no other applied force or anything like that, then it's going to be the same. Otherwise, it was going to be a bit of a complex problem in this case. All right, so I mean, if you're rotating this by the center, it basically becomes a cylinder. So it's similar to what I had up there. It's a cylinder, so which means that I is going to be equals to half r squared. So this one is going to roll, so there's going to be kinetic energy due to rolling. There's going to be kinetic energy on top. There's going to be kinetic energy at 0, plus there's going to be some gravitational energy, mgh. Okay, and then what happens afterwards? When it's here at the bottom, it's rolling. It's going to reach with the final rolling velocity, and then there's going to be the kinetic energy at 1 plus some mg, let's just say y0. Okay, so I'll just say here y0, which if I take this to be the ground, I'm just going to say this is going to be 0 meters. Okay, so if you do this, I mean, this just becomes half I omega 0 squared, but this is 0 anyway. I mean, there's no need to do this because this is 0, so it means that this is 0, right? So let me write it maybe so that you understand anyway. Let me use a different color. So this becomes half I omega 0 squared plus half mv0 squared plus mgh. Then this becomes half I omega 1 squared plus half mv1 squared plus mgy0. So if I substitute, this is going to be 0 plus 0 plus mgh plus half I, and then here I'm going to put v1 squared over r1 over r squared, not r1, plus half. Let me just open space, and then plus half mv1, that's what I'm looking for, squared. This one is going to be 0. All right, so I see I am going to substitute half mr squared, so this is mgh is going to be equals to, this is half, and then this is half mr squared v1 squared r squared plus half mv1 squared. All right, so the m's are going to cancel, these r squares are going to cancel, so what am I left with? This is 1 over 4 v1 squared, and then this is going to be plus half v1 squared. Okay, let's just say it's going to be gh plus 1 over 4 v1 squared plus 1 over 2 v1 squared. All right, so I mean this is like 0.75 basically, so you expect it to be equal. All right, so you expect it to be like 3 or 4 basically. Okay, this is gh, and then this is 3 over 4 v1 squared basically. Okay, and then basically this then becomes v1 is just the square root of 4 over 3 gh. Okay, so I think give you the height, so this is just 4 over 3, and then g is 9.8, and then h is 2 meters, and then you can actually find what the speed is going to be. So you can see here, because it's rolling downwards, it's going to gain some velocity. All right, and then v1 is going to be equals to, okay, so this is just going to be 5.11 meters per second. All right, so basically this is it. I think this is enough for this section, and then I will just see you guys whenever we do the second section. Please, if you like the video, please do subscribe, like our channel as well, the videos, just like the videos, click the notification bell as well. Comments, leave comments where you don't understand or you want anything, just leave comments and then I'll check them out. Then otherwise, do support us, and then I'll see you guys next time. And do read the description, because there's going to be more information on the description as well. Otherwise guys, cheers.